Let's answer the question, what is a Lie algebra? So here I have the definition. A Lie algebra, L, over field F is a vector space over F endowed with an operation from L cross L into L called the bracket or commutator. So that just means that we take one vector in L as the first argument and another vector in L as the second argument, and the bracket of the two vectors is another vector in L. The bracket satisfies the following three axioms. The first one is bilinearity, which just means that it's linear in each component, and so that should be familiar from linear algebra. And so to show what it means to be linear, say in the first component we have for all A in our field, so for all scalars in the field, and for all vectors x, y, and z in L, we can say that the bracket of the vector ax plus y with z is equal to first ax bracket z plus y bracket z, and then the other condition of linearity is that you can pull out the scalar, and so this is equal to a with x bracket z plus y bracket z. Okay, that's nice. The second condition is called alternativity, and so that means that for all x in L, we have x bracket x is equal to 0, and 0 as in the 0 vector. And so what's nice is that you can remember this as saying, if you think of the bracket as the commutator, is that intuitively any vector commutes with itself. An important result that follows from this is that if you take the vector, say, x plus y, where x and y are two vectors in our Lie algebra, then alternativity says that the bracket of these two vectors has to be equal to 0. However, if you use bilinearity, this tells you that this is also equal to x bracket x plus x bracket y plus y bracket x plus y bracket y. And we can apply alternativity again to deduce that the first term and the last term are 0, and so we see that 0 is equal to x bracket y plus y bracket x, and so in particular we have that x bracket y is equal to minus y bracket x for all x and y in our vector space. And so this is very nice because when we study the bracket, we really don't have to worry about the order in which we commute, because it's equivalent up to a negative sign. And similarly, from alternativity and bilinearity, it can be shown that if you bracket with anything, any vector with 0, you get 0. So from here we can deduce that x bracket 0 is equal to 0 for all x in L, which is an easy check, and I leave that to the viewer to verify. The last one here is probably the one you haven't seen before, and it's called the Jacobi Identity. And what that says is that for all x, y, and z in L, x bracket with y bracket z plus y bracket with z bracket x plus z bracket x bracket y is equal to 0. And so this provides a lot of the structure for the bracket. And you might be wondering, how do I remember this identity? And the easy way is that it's just cyclic. So you have x, y, z, and then you bump the x to the back and it becomes y, z, x, and then you bump the y to the back and it becomes z, x, y. And so the Jacobi identity becomes pretty interesting later on as we study something called the adjoint representation. And so keep this one in mind, and it's probably the one you'll have to verify if you want to check something as a Lie algebra, because the other two would probably be obvious. And so these are the three axioms we need to make a vector space into a Lie algebra. And so basically it seems pretty simple, but what's really nice is that this bracket provides a lot of structure to Lie algebras, and as we develop the theory, we'll see that. And so it would be wise to look at some examples, and so I have some examples below. So you've probably already seen an example of Lie algebra. If you take the vector space R3, and then you define the bracket to be the cross product, so that is to say that if you have two vectors v and w, then the cross product, the bracket, excuse me, is the cross product of these two. So we define it as v cross w. Then one can verify that this is indeed a Lie algebra. Of course, bilinearity follows immediately from the cross product, and so does alternativity. And so the last one that really needs to be checked is the Jacobi identity. And so I won't actually check that explicitly, but what we can do is we can check it on the basis vectors, and we can deduce that by bilinearity it has to hold for all the vectors in the space. And so let's just check it on I, j, and k, where I, j, and k are your standard basis vectors of R3. And so there are more combinations. For example, we could check it on the Jacobi identity on, say, I, and k, or I, k, and k, and numerous other combinations. But the most revealing one would be to just check on these, and then you can do the others to show that the Jacobi identity holds for all the combination of the basis vectors, and then from bilinearity it holds for the entire space. And so let's check the Jacobi identity. So we want to check that I bracket with j bracket k plus, now we bump the I to the back, so j bracket k bracket I plus, and now we bump the j to the back, and so it becomes k bracket I bracket j. Of course, now if you should have these by heart, and that is j bracket k is I, so you get I bracket I, and similarly plus j bracket j, and plus k bracket k. And so by alternativity, of course, this is equal to 0 plus 0 plus 0, which is 0. So R3 in this one case satisfies the Jacobi identity, and so I hope you believe me that with the cross product it satisfies the Jacobi identity in general, and so this is a Li algebra you've already seen before. Another Li algebra you've already seen before are the n by n matrices over a field F, where we define the bracket as x bracket y is equal to x times y minus y times x, where here we're inheriting the matrix multiplication associated with n times n by n matrices. And we'll look at this later, but this is one of the most important Li algebras, and it's one of the ones we'll study a lot. In fact, even the book says they kind of arise, the study of Li algebras kind of arises naturally out of the study of this set of matrices. In particular, there's always an identification with n by n matrices if you fix a basis with a vector space of dimension n. And so equivalently, we can identify n by n matrices as elements of the endomorphism ring of vector space. And so this would be all linear transformations on V, and similarly we just define x bracket y in that space to be in terms of composition. So x composed with y minus y composed with x. And so this, of course, is another endomorphism of V. All right, so that is another one. The third example are the abelian Lie algebras. These are really not that interesting in their own right, because you can just any abelian Lie algebra is just you take a vector space V, and then you define the bracket of any two vectors v, w to equal 0. And so it's the reason we say it's abelian is because every vector commutes with every other vector, if you think of it as in terms of the commutator. And I want to go back to example 2 here, which is why we call it the commutator, right? Because this is the traditional notion of a commutator. But that's not to confuse the bracket as this definition in general, right? This definition is only true for n by n matrices. But that bracket itself is an abstract object, and as long as it satisfies the 3 axioms we listed, then that bracket can be used. It doesn't have to be xy minus yx, because, for example, if you had an arbitrary vector space, xy minus yx doesn't even make sense. What does it mean to multiply 2 vectors? And so abelian Lie algebras, coming back here, are pretty important when we look at them inside of other algebras, because then we can deduce structure about certain Lie algebras. But in general, an abelian Lie algebra by itself isn't that cool. All right, and then last example was the 2D non-abelian Lie algebra. And so if you have a vector space V is equal to the span of, say, 2 vectors x and y, then we can make this a Lie algebra by defining the commutation relation on the basis vectors to be x bracket with y is equal to x, right? And this will, in fact, define a two-dimensional non-abelian Lie algebra. And furthermore, it's actually the only non-abelian two-dimensional Lie algebra. So there's only two 2D Lie algebras. And I just want to be clear here, and this should be a definition, that this is a relation between the basis vectors, and then all other relations follow naturally from bilinearity. So this is what this is not saying is that if you bracket two vectors, then you just pick out the first component. That's not what it's saying. What it's saying is if you bracket in specifically the basis vector x with the basis vector y, you get back x. So if you were to bracket, say, y with x, right, y bracket x is equal to, by our thing, minus, by our identity earlier, excuse me, is minus x bracket y, and so this would be minus x, because this would follow from this identity here. And of course, there are many, many other Lie algebras. The ones that will be of most interest will be the semi-simple Lie algebras. That's what we'll spend a lot of time talking about. And that's basically a few examples. And so let's look at some related concepts to Lie algebras. And so here we'll talk about isomorphisms and subalgebras, and then we'll call it a day. And so two Lie algebras, L and L prime, over the same field F are said to be isomorphic if there exists a bijective map between them that preserves both the vector space structure and the bracket structure. We call that bijective map an isomorphism of Lie algebras. So really what this is saying is that these two things are really the same up to some renaming of their elements. And so suppose we'll say that phi is a map from L to L prime. If you want to check that phi is an isomorphism, there are four things that need to be checked. The first thing is that is the map 1-to-1. 1-to-1. If you satisfy this, then you have your injectivity, and then you need to check is it on 2. And so if it's on 2, then you have surjectivity. So this is just a bijective map. Now we have to check if it preserves the vector space structure, and we have to check if it preserves the bracket structure. And so the vector space structure, right, we have to check two things in here. First of all, does it satisfy for all scalars in the field? Does A times phi of x equal, excuse me, I meant to say, does phi of ax equal A of phi of x for all x in L? So that's the first condition. And then furthermore, for all x and y in L, do we have phi of x plus y is equal to phi of x plus phi of y? And so if we satisfy these two, then we preserve the linear structure. And then the last thing is the bracket structure. And so this is where we have this being an isomorphism of Lie algebras and not just the vector spaces. And so in order to check that the bracket structure is preserved, well, we need that for all x and y in L, if you take phi of the bracket of x and y, it should equal the bracket in the other Lie algebra, which I'll denote as with the prime. So it should be phi of x bracket phi of y prime. So this prime is associated with L prime, and the bracket here is associated with L. And in general, people just eventually stop distinguishing the two because it becomes obvious from context, but I wanted to be explicit here. And so you want to make sure that phi satisfies this. If it satisfies these four things, then it is an isomorphism of Lie algebras. The last concept we have here is the notion of a subalgebra. And so we say K is a subalgebra of L if K is a vector subspace of L, and for all x and y in K, we have that x bracket y is also an element of K. And so what that's basically saying is that if we just zoom in on K and we just interacted with stuff in K, we always end up back in K. And so it's as if L didn't even exist outside of it. And so pictorially it'd be something like this, right? if you had L here, and if you had K here, and you had vector X in K and vector Y in K, and you take the bracket, it also ends up in K. That's all that's saying. So we can kind of study K separately from L. And so K is a Lie algebra in its own right. So there are some examples. The trivial examples are the zero Lie algebra, because if you bracket anything here, it's going to end up back as 0, because there's only a 0 in here. And then, of course, L itself, right? So these are like the trivial subspaces of L. And then a non-trivial example would be if you take a vector X in in L, then we can let K is equal to the span of X. And because X bracket X is equal to 0, we have that this is a subalgebra. And so K inherits the bracket operation from L. And so those are all the things that we'll talk about in this video. We will progress with the next section in the book in the next video. Thanks for watching.